This podcast is brought to you by LMU Munich.
So we saw last time that we have a master equation to write the amplitude as a sum over a certain integral basis. And there are rational coefficients of the integrals and possibly rational terms in addition. And all those terms are precisely rational in spinor variables associated with the external legs. And we saw a version of unitarity where we isolated two propagators at a time. And that allowed us to pick out certain subsets of these integrals. And then we had to do some additional algebra to essentially do integral reductions in the same way that you might have done integral reductions if you're starting from Fineman diagrams. Now, I believe Pierpaolo is going to show you a little bit more about the derivation of the basis itself at one loop. So I won't do that unless there happens to be time left at the end, which I really doubt. And then I may come back and show you a little bit more about how one actually derives the basis. But at one loop, and again, we're working, just to make things easier conceptually, we're working entirely in a massless theory. So all the internal lines in these integrals are massless. We have a variety of boxes, and we're going to consider the sort of general case where we have at least 5 legs on the original amplitude. We have a variety of boxes, and I think the notation should be self-evident, but I'll explain it in a minute anyway. So we have 1-mass boxes, so-called easy 2-mass boxes, hard 2-mass boxes, 3-mass boxes, and 4-mass boxes. So we're working in a context where all the particles are massless, so the internal lines are massless. But when we do integral reductions, of course, we can end up with arguments to each of these integrals that are sums of the original momenta in the problem. And that's what I'm denoting here by these multiple lines. So these legs can be massive, or there can be single lines left over. These are single massless momenta that were original arguments to our amplitude. They can also end up as arguments to the integral functions. And that's denoted here by single lines. And so we can have a variety of patterns. These are actually all the patterns of masses we can have for the boxes. It might be better to turn off the screen. Actually, I should do that myself. Sorry. Yeah, there we go. Similarly, there's 3 kinds of triangles we can have. 1-mass triangles, 2-mass triangles, and 3-mass triangles. And finally, there can be bubbles. Here there's no choice. The bubble always has a massive external leg. Does anyone know why? The question is, why do we not have massless bubbles? In dimensional regularization, yes, correct. So let's actually just take a quick look at one of these integrals, which if we're lucky will appear right over here. So this is the so-called easy 2-mass box. It's called easy for historical reasons because you can actually derive, it's a Fineman parameterization which can be integrated to all orders in epsilon very easily. That's not true for the hard 2-mass box. Let's see here, where is the laser pointer? So this is integrated in dimensional regularization. So 4 minus 2 epsilon dimensions. There's 4 propagators. And as I say, the way that you can do this is simply to do a Fineman parameterization. You do a clever one, actually, where you combine opposite lines first and then combine the result. And that gives you an expression you can integrate in terms of hypergeometric functions. And if you then expand that in epsilon, you discover that you have the leading term is a 1 over epsilon squared, or at least it appears to be a 1 over epsilon squared. The 1 over epsilon squared in the virtual corrections is coming from an overlap of soft and collinear singularities. The collinear singularities, remember thinking back to the first lecture where we saw them in the real emission context. In the virtual context, they appear as poles in epsilon. Likewise for the soft singularities. And in principle, when they overlap, you can get a 1 over epsilon squared, and that's a generic feature of gauge theories at every order in perturbation theory. The leading singularities will have an additional power of 1 over epsilon squared. And I say appears to because actually in this particular integral, if you start expanding these objects in epsilon, you'll see that I have 1 plus 1 minus 1 minus 1. So in fact, the leading singularity cancels. And that's not actually all that surprising. If we had a little bit more time, we would go through it. So in fact, the leading singularity here is going to be a logarithm of, let's say, s over m2 squared divided by epsilon. That's really just a collinear logarithm. In addition to logarithms, which are functions that I expect most people here have known since childhood, there's also dialogues. Does everyone here know what a dialogue is? Who does know what a dialogue is? Who doesn't know what a dialogue is? Okay. So learn to like polylogarithms. Dialogues are the simplest of these functions. These are essentially iterated logarithmic integrals. So if a logarithm you would get by just doing a dt over t integral, then, well, in that case, you'd want to go from x to 1. But here, if you essentially iterate that integral, then you'll get a dialogue. And if you iterate it further, you'd get trilog, tetralogs, and so on and so forth. And you can also get more generalized ones, which I won't show you here, where there are multiple arguments. And in a sense, you're doing integrals in multiple directions. So there's a variety of dialogues. The other thing, the feature that's worth pointing out is that there's this kind of strange looking denominator. And this is not a pole. So you're wondering maybe what is this object doing here? After all, at tree level, we expect only poles to show up as singularities. And OK, loop level, maybe things are a little bit different. There are branch cuts and so on and so forth. But this appears to be a new kind of singularity. In fact, it's not really there. And you can see, for example, one of the things about the dialogue is that you can see if I take x to 0, here a dialogue of 0 is 0. And you'll notice that if I combine terms here, that the numerator is exactly what appears in the denominator here. So this dialogue vanishes when this vanishes. So in fact, in this term, for example, that singularity is spurious. And you can use dialogue identities to show that it's also spurious elsewhere. So in fact, the term inside braces, actually order by order in 1 over epsilon squared, will vanish when this object vanishes. So this is an example of a spurious singularity. It seems to be there, but it's not actually there when you expand it. And life is full of these things. And sometimes the cancellations can be more intricate across different integrals. OK, so I think that's all we really have to.
Can you tell us what M2 and M4?
Oh, I'm sorry. So this is the easy 2-mass box. If we look at the picture, then actually I've drawn it here with M1 and M3. But if we label 1, 2, 3, 4, then M2 and M4 are simply the masses of the 2 massive legs in this box. So this, is that clear? Let me label it. Let me label it explicitly here. 1, 2, 3, 4. So again, 1 and 3 are massless legs, and 2 and 4 are massive legs. So M2 squared is simply it's.
Yeah, well, the K1 and K12 and K123 that appear on the left-hand side?
Yeah, so for example, in this case, m2 squared would simply be equal to k2 squared, and m4 squared is simply equal to k4 squared, which is equal to k123 squared. Okay. Let's go down. Okay, so that's the set of integrals we have. And our goal is to identify the coefficients of each of these integrals. What we were able to do last time is we looked at a certain cut where we're isolating, insisting that there be two propagators there. And of course, those two propagators, there could be a variety of boxes. I could shift legs from here to here. So some of these boxes will show up, some of these boxes. In addition, some triangles will show up and some bubbles as well. On the other hand, there will be some integrals that, for example, can't show up. So I'll be picking out a subset of them, and then I'm doing the reduction algebra that would be analogous to the kind of tensor reduction that you do if you're doing Fineman diagrams in order to isolate the coefficients of each of the integrals. Now, today we want to go beyond that. First, though, we should just think a little bit about the roles of dimensional regularization. And this is, again, more of a kind of a conceptual understanding. So the claim is that working in dimensional regularization, we'll really be able to extract the entire amplitude. And it's essentially a very sophisticated way of doing dispersion relations. It's true that I'm not actually doing a dispersion integral explicitly, but implicitly I'm going from a phase space integral to a loop integral. And if you think back to the original version 0 of the unitarity method, then there was this subtraction constant. And that subtraction constant was associated with the fact that there's bad ultraviolet behavior, there's an ultraviolet divergence in the object that we're trying to integrate. So the first thing that dimensional regularization is doing for us is it's acting as a UV regulator. And in this standard fashion in field theory. So once you work in dimensional regularization, there aren't any ultraviolet divergences. You're trading them in some sense for poles in epsilon, but as long as epsilon is non-zero, it is actually maybe a large, but a finite number. The thing that's actually more important from a practical point of view when you're doing these calculations in QCD, and we've seen an example of that already in this easy two-mass box. The easy two-mass box, you can convince yourself very quickly by power counting, is ultraviolet finite. And yet there are still singularities in epsilon. Those singularities are infrared. As I explained, they have to do with the soft and collinear structure. So it's acting as an infrared regulator. And we're going to be using dimensional regularization for the singular terms in real emission. That will be a separate set of lectures, but you've seen a little bit of a flavor of that in the first lecture. And it's also acting as an infrared regulator in the virtual corrections. And all these integrals are going to, in general, have poles in epsilon. These guys have just 1 over epsilons. This one is actually finite. And these two integrals have genuine 1 over epsilon squares. The same is true over here. There's a 1 over epsilon squared. This is 1 over epsilon, and this one is finite. And this one has an ultraviolet 1 over epsilon. In fact, that's the only source of ultraviolet 1 over epsilons at one loop. In the context of unitarity, there's actually a third role that dimensional regularization is playing, and it's linked to its role as an ultraviolet regulator. So what it does is it removes the ultraviolet divergence, so the integrals become convergent, and as a result, there's no subtraction ambiguity in dispersion relations. So at least conceptually, that's the reason that we're able to reconstruct the entire amplitude, is that the issues that we would otherwise have are taken away by dimensional regularization. Now, there's also a slightly more down-to-earth way of looking at that. If you remember, again, the version 0, in some sense, of unitarity was going from a branch cut to a logarithm. So reconstructing a dispersive part from an absorptive part. And, well, the integrals are fine. All these integrals have branch cuts, and so we can see once we remove the subtraction ambiguity how it is we'll be able to uniquely reconstruct the logarithm, in a sense, or the dilogarithm from branch cuts. But what about those rational terms? Rational terms clearly don't have branch cuts. How am I getting a handle on those? And we're not going to have time, I think, to see that explicitly, but if you do unitarity in 4 minus 2 epsilon dimensions, you can certainly get at those. And the answer is that when we're working in dimensional regularization, of course, we have to change the dimension of the coupling. We're shifting slightly away from 4 dimensions. And what implements that shift in the coupling is that there's always some power of some invariant to the minus epsilon that comes in front. So whatever the amplitude was, whatever the expression was in 4 dimensions, there's going to be an additional factor of minus s to the epsilon in front. And of course, that factor is not going to be inert. It's going to give rise to a variety of logarithms, which are then also important in terms of scale running and things like that. But when we now expand, so if we have a rational term now, it's really secretly multiplied by minus s to the epsilon. And you'd say, so what? There's no poles here, and I'm going to take epsilon to the 0, and so then this just disappears, and I'm left with my rational term. But if we're working in 4 minus 2 epsilon dimensions, in a sense, we're working to higher order in epsilon, and at that order in epsilon, all of a sudden, lo and behold, we now have a logarithm. So by peaking one higher order in epsilon, we all of a sudden have a branch cut. We can reconstruct this complete object, including its rational prefactor, and we then realize that this is really reconstructing minus s to the epsilon. We take epsilon to the 0, and we're left with the rational term that we're interested in. So that's the role of dimensional regularization. And so we now want to move on from unitarity to generalized unitarity. So far we've been picking out contributions with 2 propagators. We've been insisting that there be 2 propagators in every contribution. You might wonder, why not insist on more? Can we cut more lines instead of just cutting 2 lines? Can we, for example, cut 3 lines? So that would be our ordinary unitarity cut. Now let's cut a 3rd line. Well, what would be the advantage of that? Well, one advantage is very clear. If you cut 3 lines, you can't have any bubbles, so we don't have to worry about removing the bubble in that channel. Moreover, once you cut 3 lines, instead of having multiple triangles, so having, let's say, some combination of 1 and 2 mass triangles, you'll only have a single triangle. You'll still have boxes, but there'll be fewer of them because there's fewer boxes that share 3 propagators compared to just 2 propagators. And do we have enough degrees of freedom? Well, we're essentially, as far as the cutting is concerned, so the if you think back to how we were doing things yesterday, then the algebra and the structure of the propagators we're treating in 4 dimensions. The loop integral we're then doing in 4 minus 2 epsilon dimensions. So in 4 dimensions at one loop, we have 4 degrees of freedom. There's 4 components. There's 4 components of the loop momentum, L. So in fact, we could imagine not just cutting 3, but even 4 propagators. And that would be very nice, because then, in fact, if we were able to do that, we would have no triangles at all. We'd just have boxes. And in fact, we'd have a unique box, because there's only one box that has 4 specific propagators. So then we'd really be getting a step closer to picking out a single element in this sum and assuming that we can do something with that expression, the quadruple, so-called quadruple cut. We'd be directly extracting the rational coefficient of that box. So let's go ahead and do that. So let's start, and let's, for the moment, just ignore the question of infrared singularities. We already know that by then taking the loop integral into 4 minus 2 epsilon dimensions, we can control all of that. So we have write down our box integral. And again, just as a notational device, let me remind you that ki dot j is just the sum of momenta from I to j. So k12 is k1 plus k2, for example. Okay, so we saw last time how we do cuts. We replace propagators by delta functions. So let me do that. And let me be a little bit sloppy about factors of I and 2 pi to the 4th. Just cross that out and really just focus on the delta functions themselves. Okay, so we know about delta functions that what they're trying to do is they're trying to localize the integral. We have essentially the integral over a delta function is going to constrain each of the components to solve the equation. We have 4 delta functions, so there's 4 simultaneous equations that we need to solve. Yes?
The plus means for the positive energy.
The plus is I'm just copying what we did last time. Yes, it means the positive energy. And if you're a little bit puzzled by that, then just hold that thought for a few minutes. I mean, we've learned how to do a cut, and I'm just blindly applying that idea to extending from 2 to 4 cuts. So the question is, how many solutions do we have? We have 4 quadratic equations. That we need to solve. And it turns out that the counting solutions of multivariate polynomial, higher degree polynomial equations is actually a fairly non-trivial thing to do. But here we can observe that we can take linear combinations of these equations. For example, we can subtract this one from this one. That's going to leave us with an equation that's only linear in the loop momentum. And likewise, we can subtract the original form of the second equation from this one, and that will give us 2L.K2 plus S12 minus K1 squared equal to 0. And again, here we can use momentum conservation and then subtract the very first equation, and we then have three linear equations and one quadratic equation. And in this case, it is easy to count. We expect two solutions. Let's actually solve these equations. Let's do it explicitly. And let's do it explicitly in the case that legs 1 and 4 are massless. So we know that L is going to have to be a massless vector, and so we can write down a general form of a vector like that. Let's see here. So we can use our spinners to write down a null vector. And this is a nice choice because, of course, the first equation, this vector is null, so is automatically satisfied. If we dot it into K1, and then we see we're going to get an angle product of 1 with 1, so that'll automatically be satisfied. If we dot it into 4, then we're going to get a bracket product of 4 with 4, so that's automatically going to be satisfied. And we have one more equation that we can impose. It's the third equation. And when we impose that equation, we'll find that S12 is equal to Xc over 2 times 1 to 4. So we can then solve for Xc. If leg 2 happens to be massless as well, then we can further simplify this result by dividing out by the angle product of 1, 2 on both sides, but that doesn't really matter. In any event, we have a solution for Xc, and we would find that our vector is, let me write it in the form that, so we have S12 divided by 1, 2, 1, 2, 4 times 1 mu 4. And similarly, there's also going to be another solution which is given by minus S12 over 2, 4, 2, 1 times 4 mu 1. So we have our two solutions. I'm sorry, the second equation has? Yes, so I dot K2 into here. That gives me 1, 2, 4, and that thing is supposed to be equal to S12. And that's what fixes the normalization C. So we have two solutions, but there's a problem. The problem is that, of course, vectors 1 and 4, and therefore spinners 1 and 4, they're completely unrelated. They're certainly not complex conjugates of each other. That means that these solutions are complex. But the domain of integration here, let's ignore the Fineman I epsilon for a second. The domain of integration here is the real slice. The components of L are real. And if we think about defining a delta function as some delta convergent sequence of Gaussians or Lorentz or 1 over x squared plus a squared type functions, then if we plug in a complex value here, whatever the way we define the delta function, we're going to get 0. In fact, the notion of a positive energy, I mean, what does a positive energy when the energy is complex mean? It doesn't mean anything. So we have our two solutions all right, but they don't lie in the domain of integration of the delta function. And so this quadruple cut is going to give us 0. And ultimately, if we were to apply it to the other side of the equation, we'd also get 0. So we would derive a true equation, but one that is not very useful. So what are we going to do here? Well, it turns out that the right thing to do is to ignore this problem, essentially. That's the way it was done originally. And just pretend that the delta functions are allowed to have complex solutions. Actually, that turns out also to not be correct when you go beyond one loop. So what we really need to do is to reinterpret what we mean by the delta functions and what we mean by cutting. And the way we're going to do that is we're going to replace these delta functions by contour integration. It's really the more natural kind of object. The way you localize an integral in a complex space is not by imposing a delta function, but it's by doing a contour integral. Because when you do a contour integral, you're essentially picking out the value of the function at the pole. You're localizing it at the pole. So how does this work in one dimension, one complex dimension? We're going to have some contour integral. And it's going to be a little circle around some point, which I'll call z0. And that means I have some circle of some small radius, delta. I won't be very precise about what I mean by delta here. So we notice that if we do a contour integral like that, and let's suppose we have some polynomial, let me get the indices right here, in z in the numerator, and we have polynomial 2 in the denominator, where this equation has only a simple root at a. So the definition of z0 is this implicit equation, so that this object, in fact, has a simple pole. This denominator has a simple pole at z0. So we want this thing to go essentially when near values of a, near z0. So we know how to do this integral. We're simply going to get the numerator evaluated at z0, and we're going to get a Jacobian in the denominator. So remember that if we were doing a delta function, some real delta function, delta of f of x, then we're going to get, of course, a sum over of the solutions of f of x equals 0. And we're going to get 1 over the absolute value of f prime of x where that solution happens. So it's a very crucial difference here. That crucial difference is the absence of these absolute value signs here. There's no absolute value here. You do a contour integral of an analytic function, you get an analytic function. And it's actually a crucial difference, and this is actually the correct way to think about it, and not this one. So you could imagine having some complicated definition of a delta function that extends into the complex plane and all that, but that's not what you want to do. You don't want those absolute values. So when I write down a delta function now, then what we're going to do is define what we mean by the delta function. So this is a new kind of complex delta function, no positive energy condition, and we're using the same symbol as we would for a real delta function, but what we mean by this is this contour integral around the solution of the same numerator and with a denominator that localizes the integral at the pole. So when we do this, we now have to do this not in 1 complex dimension, but in 4 complex dimensions. And the theory of multivariate complex integration has a lot of subtleties, but which would take us too far afield to even talk about. But if you imagine simply taking a 4-fold version of this, so instead of having a circle, we now have a 4 torus that encircles the simultaneous solutions. That's the contour of integration we want. And these simultaneous solutions are called global poles. One way of thinking about it is that you want to choose a parameterization for the loop momentum where you can factorize the denominators into a product of single poles in different complex dimensions, and then you can imagine simply doing the contour integrals independently in each of the dimensions. And of course, part of the process of doing that, the change of variables you need, will yield a Jacobian factor that's analogous to that derivative of polynomial 2 in the denominator. So if we want to think pictorially about what we're doing, we started out with a loop integral where, at least for the L0 component, it's easy to draw the contour of integration and where the poles actually are. We're integrating along the real slice. Maybe I should use colored chalk here. Integrating along the real slice, and the poles, which would otherwise be on the real slice, are slightly shifted away by the Fineman I epsilon prescription. And we're replacing that contour of integration in a certain sense in each of the components, although one has to do, as I've said, a change of variables first. We're replacing that by an integration around the global poles, which are sitting way off in the complex plane. They're nowhere near the real slice. So we're simply replacing it In this case, we have two solutions. We're going to replace it by a contour integral around those solutions. This is not a contour deformation. It does not leave the value of the integral unchanged. In fact, what it's going to do is take us from the integral, which has dialogues and branch cuts and stuff like that. It's going to take us and give us a rational function which is very closely related to the coefficient. And the reason we're doing this somewhat obscure looking operation, if I had simply started my lecture yesterday with this construction and said this is unitarity, then I think most of you would have wondered, what is this guy talking about? But I think you can see why this is essentially an operation of cutting and what the connection with unitarity is. So let's go back and do something useful with all this construction. Let's apply this cutting idea. So we have, if you can imagine writing the amplitude in the abstract as a sum over Fineman diagrams and the Fineman integrals. So we have these loop integrals on both sides of the equation. We start out with an object where we have an integral along the real slice, and on both sides of the equation, I want to make this replacement. I want to replace the contour along the real slice with a 4 torus encircling the global poles. And so I want to apply quadruple cuts to both sides of that equation. So when we do the change of variables, when you do a parameterization of the loop momentum, of course, there's going to be a Jacobian there. That's going to live in the numerator. When we actually localize on the global pole, there's going to be another Jacobian in the denominator. At one loop, those turn out to be essentially constant that is just dependent on the external invariance. So we don't actually have to work them out in detail. On the left-hand side, we get a Jacobian. And that's going to be multiplied by a certain sum over the solutions of the equations, or equivalently, the global poles in our new language. And then, as usual, when we cut a line, we have to sum over all the intermediate states that can go in. So we have to sum over helicities. But now it's not enough just to sum over helicities, because we don't know the identity of the particle that can be circulating around the loop. So we also have to sum over the different kind of species that can circulate in the loop. And we'll have a product when we isolate certain 4 selected propagators and we put them on shell. Well, what that does let's see here. We're going to get a product of 4 amplitudes, because these lines are now on shell and they're on their physical states. Let me just label these A, B, C, and D. Now, in this particular picture, I've drawn them as all being massive, but they don't have to be. They could be, for example, we could have leg C being massless. And then what do we have here? We have our old friend, the 3-point amplitude. And everything is very nice because these momenta, remember our solutions are complex. So I've of course only shown you one of the loop momenta, but you can imagine when you shift that complex momentum by the external momenta, which are real, then in fact all 4 of the cut loop momenta are going to be complex. So these 2 guys are complex, and everything is fine. We can find a non-vanishing value for our 3-point amplitude. So we can treat all the different boxes, whether the external legs are massive or massless on the same footing. So we've cut apart our loop amplitude into 4 tree amplitudes, and we have to take the product of those things and sum over helicities and species, and that is going to give us the left-hand side of the equation. Now, on the right-hand side of the equation, there's a specific integral that's been picked out. Exactly which one depends on which global poles we've chosen. Different boxes will have different global poles, and of course, we're going to have to iterate over all of them in order to find all the coefficients. On the right-hand side, of course, we have the coefficient. It doesn't care about global poles or anything. It's just a rational function sitting in front. And we have, of course, the same Jacobian. And we have nothing in the numerator, so we're just going to have 1. We're just going to be evaluating 1. That numerator polynomial 1 is just 1. So we're going to be summing it, and that's just going to give us the number of solutions, which, as we've already seen, is 2. So we now have a useful equation because we can, of course, equate the left and the right-hand sides. And that gives us our equation for the box coefficient. One-half from the number of solutions. We have to sum over the solutions to the quadruple quadratic equation. We then sum over species and helicities of particles that can run around the loop. And we have the product of the tree amplitudes running around the loop. And this formula is very nice because you'll notice, the first thing you'll notice is that there's no more algebraic reduction to be done. I'm not having to look at this coefficient and say, oh, there's the loop momentum dotted into some external leg. Let me break that apart into a sum of propagators and then cancel propagators. This is just it. This is just directly the coefficient. Moreover, it's something I didn't perhaps emphasize, but the Behrens-Hille recursion relations, which you may have seen elsewhere, in the BCFW relations we saw, recursion relations we saw on Monday, you can implement them purely numerically, right? So we have an explicit formula, which we saw for the spinor products. You can implement those numerically. That allows you to implement numerically the formula for A3. Out of A3, we can build any tree amplitude that we want, and we can do that purely numerically. You can run that recursion relation purely numerically. You program A3, and then you program the BCFW relationship, and you can run it purely numerically. And that means that this coefficient we can compute purely numerically. There's no need to do it analytically. It may produce a more efficient formula if you do it analytically and simplify it, but you don't have to. And that is, in fact, the way that these particular coefficients are computed in Black Hat, which is one of the codes that are available now, or one of the collaborations that uses the codes to do these next to leading order computations with high multiplicities of jets. So we've eliminated the last problem that we had earlier, and we've gotten this nice bonus that we have something that's suitable for direct numerical use. So we have, if you like, a the beginnings of a numerical unitarity formalism. So before I go on, let me stop to see if there are any questions.
Yeah. So suppose I want to compute some specific amplitude. How do I know what the tree diagrams or what the tree amplitudes are that I'm looking at?
Very good. So let's imagine that you're trying to compute within the spirit of what we're talking about here. And in fact, we'll do some examples in a little while. But let's imagine you're trying to compute the one-loop corrections to a 6-gluon amplitude. Okay. Well, with 6 gluons, then I can't get any 4-mass boxes, and I can't get any 3-mass boxes either, because I just don't have enough external legs. So my list of boxes includes 1-mass boxes, easy and hard 2-mass boxes. So for example, I might have a box that has 1, 2, 3, 4, 5, 6. And I might have a box that has 1, 2, 3, 4, 5, and 6. And there are lots of other possibilities. You have to include all possible boxes that can actually show up. Okay, so in general, of course, I have to have amplitudes here, not just diagrams. So let me fill in all these corners. And now I'm going to apply the quadruple cut. Let me take this box as an example. So we're going to apply a quadruple cut. And what I'm instructed to do is to collect a list of all the tree amplitudes that appear going around this loop with all the different helicity configurations. I have some helicities for the external legs, but let me not worry about exactly what they are. Whatever they are, then I have to collect, for example, the positive and negative choices for helicities here, positive and negative choices for helicities here. We know that some of these vanish. And of course, if any one of these 4 amplitudes vanishes, you don't need to compute the rest. But some of these in general will be non-vanishing. And some of these you actually know how to write down without thinking about it, because in the 3-point case, of course, there isn't any sum of diagrams if we're starting from Lagrangian. There's just the 3-point vertex. So I have to collect the various 4-point amplitudes with whatever the helicities of legs 4 and 5 are. So for example, if we have 4 plus 5 minus, there's going to be 2 different amplitudes that we need over here. If both of these, for example, are negative helicity, there's only going to be 1 amplitude that we need to collect. So knowing the identity of the external legs and their helicities, we then have to take all possible choices of the internal helicities and also internal species. So here I've been implicitly saying this should be a gluon, but if we're now going to QCD, where we also have quarks, and let's say massless quarks for the moment, then we also need the amplitudes where you have a 3-point amplitude with a fermion pair and 1 gluon, again, that you can compute from the basic vertex in the Lagrangian in the same way that we did it for the 3-point vertex. And you need the amplitudes with 2 gluons and a fermion pair. Is that clear to everyone? Not clear. Another question?
Yes, so the inherit cut has a nice physical interpretation, as its name suggests. So, is there any kind of insight into what physical interpretation might be about a higher inherit cuts? Apart from just being able to do them and get results?
I think people have tried over the years, but I would say I don't find it very convincing. And to me, I think the sort of exposition that I've given over the last 2 lectures is the best intuitive understanding one can have, at least for me. You know, different people can have different intuitive understandings. So there is old literature for the 1960s where people used exactly the term generalized unitarity, where they're, in a sense, cutting multiple legs, and you can relate that to sort of properties of amplitudes off in the complex plane, except at the time people weren't thinking about complex momenta, they were thinking about complex invariants. And I don't find any of that really very intuitive or convincing, because it's, I mean, yes, it's in some sense related to properties of the S matrix off in the complex plane, but that's not something which I have an intuitive feel for. Yes?
So those global poles, they actually were present in the original integral as well, right?
Absolutely. I mean, they are, if you look at a box integral, those global poles are sitting off in the complex plane. They're complex solutions of the loop momentum where there's a quadruple pole in the integrand. And there's a certain sense which, to make mathematically precise, is still an open research problem, is to how is the specific branch cut structure that we see determined by what, if I may use a fancy term, by the algebraic geometry of those global poles. Question?
And someone in the first lecture mentioned that we are still dealing with Fineman diagrams, yeah? So there should be like thousands of them. Is this categorization?
So the way I want you to be thinking about Fineman diagrams here is that it is a possible representation for the amplitude. You should never calculate with them explicitly, but if you want to make general arguments based on the structure, then it's a useful tool and you can use it for making general arguments. So when I say, for example, that the filled in graph here represents the sum of all Fineman diagrams, it's just so that you have a mental picture, you know what that object is, you know how, in principle, how to compute it. In fact, today I would probably say, well, this is the amplitude, and you should think of it as being computed by the BCFW on-shell recursion relations, right? It's the same object. One of them, I think, is a much more practical way to compute things if you want an explicit result, excuse me. Whereas, but for example, in terms of arguing about the large Z behavior, it's sometimes convenient to think about how, in the abstract, it would look if you were doing it by a sum over Fineman diagram. So I think that's kind of the conceptual role that I would encourage you to have for Fineman diagrams in your thinking.
In the zero unitarity,
Version 0.
in the
Yes.
version 0, as you mentioned,
Yes.
unitarity, when you do that, you want to calculate the integral, right?
So in version 0, you actually have to calculate these integrals,
Yes.
which is here. The idea here is the integral. Well, I mean, the first person, let's say, who goes to 3 loops, and then that person has to sit down and calculate these integrals. They don't come from the sky, but these box integrals were, I think the complete list of them, even with internal masses, was essentially calculated by 't Hooft and Veltman probably sometime between 35 and 40 years ago. So today you can just look them up. But in principle, the idea is if you're really starting from 0, you do this calculation once instead of every time you're doing an amplitude, and that's it. Then it's just part of your list.
But could you use something like more cutting, more generalized unitarity to get the result of the integral as well? Or no?
Okay, so that's an excellent question. And at one loop, the answer is yes, explicitly. And as I mentioned, there's this paper of Brandhuber, Spence, and Travellini where they actually do this. I think at one loop it's a very difficult way to do it, but it demonstrates that it is possible. I would like to believe that in principle it's possible at higher loops, but I don't know how to do it explicitly. So that's also, if you like, an open research problem. Not sure that that's a problem I would encourage a student or postdoc to tackle, but it is an open problem. Whereas some of the other things that I've mentioned are open problems are good things to tackle. Yes?
Just to make sure the sum over species does not include ghosts, right?
No. It's a sum over, when I say sum over species here, I mean physical species. Thank you for the question. I should make that. So in a sense, if you want to think of different helicities of gluons as being different species, then it's the different states, different physical states that are running around. So it would be quarks. If there happen to be scalars in the theory that you're considering, like n equals 4 supersymmetry, then you'd have to sum over those scalars as well. But it does not include unphysical states. Remember that when you have questions like that, then these cuts are putting the lines on shell. So whatever is an on-shell tree amplitude should be included. Whatever isn't doesn't belong there.
You define the maximum cut by replacing with the center point. So what do you do with other cuts?
I'm sorry, what do I
Do
do?
you have another formulation for other sorts of cuts, but not for less than maximum?
We will at least get to see how one proceeds there along the broad lines, although I don't think I'll have time to do an explicit derivation there. But the short answer to the question is that what often happens is that when you're doing the first set of cuts, you get additional analytic factors which allow you to further localize the integral and then have, in some sense, additional cuts that are hidden. That's the way, for example, things work in a lot of two-loop cases, which are more non-trivial. Let's just quickly sort of go from what we've been doing here to really a complete amplitude, or at least understand that it's possible to do that. So here I've been implicitly thinking about having a fixed ordering of the external legs. So there's a fixed color ordering. And that corresponds with the fixed color ordering that we did at tree level. We had a color decomposition. And from the color-ordered subamplitude, certainly if we have it in an analytic form, then it's easy to go to the full amplitude. But nothing says that color decomposition is the same at tree level as at one loop. Did Pierpaolo already discuss this? Okay, so I won't have time to derive it, but basically, if you want to go through the derivation, it's the analogous derivation to what you do at tree level. You unwind all the FABCs, except now you have to include one-loop graphs. So if we have a one-loop amplitude, then it's, of course, a function of the external spinors and helicities, and it's a function of the color labels. And I'm simply going to write down the form of the color decomposition. We now have different spins and different species in principle that I'm all going to group under this label J that circulate in the loop. We have a number of different color structures now, which I'm going to label by this index C, that go up to the floor of n over 2. Is everyone familiar with that notation? What this object means? It's the largest integer that's less than or equal to x, for those of you who haven't seen it before. There's, as at tree level, there's a sum over a certain set of permutations, and I'll define what I mean by Sn semicolon C in just a minute. There's a group theory factor, which is a function of that permutation, and then there's a color-ordered subamplitude, which now, in addition, carries this label C depending on the group theory factor, and there's different contributions from the different particles running inside the loop. So the first color factor is easy. because, and I'll just write it with argument 1, you can easily see what the form is for more general sigma. It's just the number of colors times the tree level color factor. And this is the so-called leading color contribution, because it's the one that dominates in the limit that NC is large. And that limit, you might not think that n equals 3 is very large, but that limit actually is quite useful in QCD. It's implicitly there in all Parton-Schauer codes. It turns out in practice to be a very good approximation, at least for, let's say, in the region of 3 to 5 jets. So it's something that's actually quite commonly used. The subleading color factors have 2 traces, and in a sense you can think of this NC as being the trace of 0 charge matrices. So here we have A1 through AC minus 1, and then the second trace is AC through AN. And SNC is precisely the set of permutations leaving this color factor invariant. So in the case of the leading color terms, that's just the rotation, cyclicity of the trace. Here there's basically a product of 2 rotations, and then if the lengths of the traces happen to be equal, there's also an exchange of the 2 traces. Now, the thing that simplifies your life enormously at one loop, and that isn't completely obvious, but that you can prove by just unwinding the color, is that ANC can be written as a linear combination of different arguments to AN1s. So, in fact, what we've really learned how to do are calculate the AN1s, because these are things that have the same cyclic color ordering as at tree level. That's what this formula has been applied to thus far. We could imagine, of course, applying it directly to ANC, to where C is bigger than 1, but in fact, there's no need to do that at one loop because we can extract all the information from the leading color subamplitudes. So let's do an example. First example we do won't be quite as complicated as the 6-point example, slightly simpler. NJ here is the number of particles of spin j. So, of course, for the gluons, it's going to be 1, but you could have multiple flavors of quarks, for example, of spin 1/2. There's also the implicit assumption here that if in fact there's the implicit assumption here that everything is living in the adjoint representation for the quarks. This NJ actually is normalized by 1 over NC, so it's the number of flavors divided by NC.
Those are not quarks. If everything is in adjoint.
Yes, but I'm saying, so if they were quarks, then NJ has an additional factor of 1 over NC in them.
But what happens with they will have different T's then, right?
No, these are the charge matrices in the fundamental, so as it so happens for quarks, that's the only difference you get, just the overall NC goes away.
No quarks have the color in fundamental.
These are charge matrices in the fundamental.
You haven't traced.
Doesn't matter, right? If the quark is running around the loop, if you think about it in terms of Feynman diagrams, it's the same. So the external legs here are gluons, yes. If the external legs are fermions, again, there's a generalization of this, and I think that you know how to derive this. You can derive what that is here. So let's recall the 3-point amplitudes. That we have. So we have the MHV 3-point amplitude. And of course, its cyclically permuted friends. We have the version of the Park-Taylor equation at the 3-point level. And just as a handy reminder, in this case, of course, in order to enforce the 3-point kinematics, we have to have the bracket products vanishing so that it's the tilde spinors that are proportional to each other. And the conjugate amplitudes, or MHV bar, of course, are just given by the spinor conjugate formulae. And here it's the angle products that vanish, and it's the spinors which are proportional. And we'll also need a variety of 4-point amplitudes. And again, we know those from the various Park-Taylor equations. So one of them is non-vanishing. And the others, we also have a variety of vanishing amplitudes for various configurations that have either 3 or 4 negative helicities. See if we can pull it down. Is this line, are these lines still visible in the back? No, but I think you know what they are, so you can imagine what they're going to be. So let's do an example. And let's look at the coefficient of a one-mass box where the massive leg comes from summing K1 and K2, and the other legs are massless. And we're going to look at this in sort of simplest kind of amplitude that fits into that picture, at least with that basis. 4-point amplitudes, of course, also fit into that basis, but the box you need is the completely massless box. So it's a different basis in that case. So let's draw out the quadruple cut here. Leave enough space. So let's label the momenta here. Notice that I'm being a little bit sneaky and skipping over L2 just so that it's a little bit more mnemonic, and L sub I is going into a vertex which has leg I in it as well. So we have to do, of course, a sum over all helicities. We're just going to compute the gluon contribution in terms of internal lines here. And in principle, I should write plus or minus at each of these vertices, but we can take advantage of the fact that we know that a lot of 4-point amplitudes vanish. So, for example, if I were to write a minus and a plus here, then we have 3 negative helicities, and so that thing is going to vanish. So let's not even write out the full table. Let's just fix it immediately to be the one contribution that is non-vanishing, and I'll write in the cuts here. So that says that this has to be a minus, and this has to be a minus. And in the rest of the cases, then let's in fact put in sigmas here, stand for plus or minus. They're the helicities. And again, it flips across the cut because we're changing the direction of momentum flow. So we can make up a little table of the values of sigma 1 and sigma 2. It could be both minus, and plus, or plus and minus, and finally plus and plus. So the easiest case is where they're both minus. We can then look at the vertex in the upper right-hand corner. So we would then have a plus, and a plus, and that vertex simply vanishes. So we don't need to worry about him. Let's look at the next line, which is where it's going to be a minus and a plus. Then that would be a minus over here, so that vertex is non-vanishing. And And let's draw, though, the vertex next to it, which is now going to be a plus, and a minus, so that's also non-vanishing. But we have to think a little bit more about what's happening with the spinors here. So this is an MHV bar vertex, so these spinors had better all be proportional. So in particular, we have to have lambda 3 proportional to lambda of L4. That's from this vertex. In this vertex, we have to have lambda of L4 being proportional to lambda 4. Well, proportionality is transitive. And what that says is that for this helicity assignment to be possible, we have to have lambda 3 proportional to lambda 4. How many people here think that that's possible? How many people here can explain why it's impossible? K3 and K4 are external momenta, so they're just fixed, and in general, they're unrelated. That means that the spinors, which we can, these are our spinors for real momenta, we can construct them out of the momenta. In general, they're unrelated, they're not proportional. And so there may accidentally be configurations where this happens, but we're interested in computing this coefficient for arbitrary external momenta. So this equation is simply false. And what that means is that for a generic configuration of external momenta, one of these two statements will be false, and so one of these two vertices will vanish. That means that we cannot actually get these configurations either. This one, the same argumentation would follow, but for the vertices on the right-hand side of that diagram instead. And that's, in fact, a general principle that sequential, that is, 3-point vertices that are adjacent have to have opposite chirality. So if one of them is MHV bar, its neighbor has to be MHV. So we're now left with this object. And here we can see, so we need to flip the sign of this helicity as well. Now we can see that that rule is satisfied because we have an MHV bar followed by an MHV. And sigma 1 is plus, so this is MHV bar again. There's no constraint here on the chiralities of higher point amplitudes, because in higher point amplitudes we don't have this feature that the spinors or the tilted spinors be proportional. So we can solve for L4 in the same way that we solved for the loop momentum and the quadruple cuts earlier. I won't go through the equations explicitly, but we can write L4 in the following form as the ratio of the angle products 4, 5 and 3, 5 multiplied by the vector 3 mu 4. And we can also write down, we can now solve for the various spinors. So we have, there's 4 positive helicity spinors and 4 negative helicity spinors. And you can check that momentum conservation is satisfied and that the corresponding loop momenta are all on shell. You can also see right away that some of the identities that are required by the 3-point vertices are satisfied. I'm not going to do those checks explicitly, but I encourage you to do them explicitly yourselves. And we now simply apply our quadruple cut formula. So the coefficient of this integral is going to be 1/2 times the 4-point amplitude at the lower left-hand corner. Actually write it in a slightly different ordering. And simply multiply out the other three-point vertices around the box. Four plus 5 minus 3. We substitute in the formulas here that we have over here. That gives us an expression where, for example, we'll still have the loop momenta appearing in here. But we have the substitution formula for the various spinners. We plug those in, and then we basically are left with a little bit of algebra to do. I'm not going to do that for you, but again, I encourage you to work that out yourselves. And what we find is the following formula when all the dust has settled. And I think at this point most of you will recognize what that formula is. It's exactly the tree-level formula that you would get, and up to a sign here, which I'm not sure I've gotten right. It's It turns out, if you look at, if you think back actually to the easy two-mass box formula we wrote down, there was a denominator, which was essentially st minus m1 squared, m3 squared, or there it was m2 squared, m4 squared, but rotate the box. And here, of course, we're taking a one-mass box, so m3 is actually 0, so the denominator is st. Well, what is st in this box? It's, of course, s34 times s45. So this is exactly the denominator of that box, of that integral. That isn't at all an accident. That turns out to be, in the MHV case, the kind of general pattern. And in fact, even though I haven't told you that explicitly, secretly we've been not only doing this computation in QCD, but also in n equals 4 supersymmetry. For this particular box, you cannot have a fermion running here because it would violate helicity. Remember that helicity conservation for the fermions says that we have to have a plus and a minus at opposite ends of the fermion line. So the fermion contribution will actually vanish, and in fact, with charged scalars, there's no helicity, but you can use the charge of the scalar. The same argumentation applies. So for this particular contribution in this particular amplitude, QCD and n equals 4 supersymmetry have the same contribution. And so we've calculated it in n equals 4 supersymmetry as well. And this is, in fact, the general pattern, this kind of denominator of the box times the tree amplitude for the MHV helicities. This is, of course, very special to the Park-Taylor helicity pattern. So, as I perhaps should have expected, there won't be time to do the triangles in any great detail, but there was a question earlier, and I'll take just a few minutes to outline how things go.
Can I ask you
Yes,
for that?
sure.
Is that the other part, that the coefficient is also an MHV tree, de facto?
So that's the question is the coefficient always an MHV tree? I think that's the answer. That's the question.
Starting from an MHV pentagon, the coefficient we found that's an MHV tree.
So that's special to the. It's special to this MHV configuration, and it's in QCD. It's not in general true. There's other contributions because, for example, there will be triangles, and their coefficients are not exactly MHV trees. But in n equals 4 supersymmetry, this is a general pattern, not just at the 5 point, but at the 6 point, as long as we're looking at the Park-Taylor configuration. So as long as there's 2 negative helicities in the remaining oral plus, yes, then you in fact get a factor. All the spinorial factors, in a sense, are exactly the tree amplitude. And that's one of the things that's very special about the n equals 4 theory.
Also, what happened to the second solution of the delta function?
There is no second solution because it's essentially going to it's essentially eaten up by the fact that some of them vanish. So there's 2 solutions, but sometimes the coefficients, the product of amplitudes in a given solution can vanish, and that's essentially what happened over here.
On one hand, we still have 2, but on the other hand, we have only one solution, so we have 1 over 2.
The 1/2 is always there, but it can be, so you're supposed to sum in a sense over both global poles, but it can be that the residue in one case is 0, and that's what's happening over here. So in the minus 5 minutes that I have, I'm just going to draw one picture and tell you in words what happens in the case of the triangle. So let's think a little bit about the 2-mass triangle. So here we have a triple cut, and the way I'm going to explain it here is not exactly the way it's in the literature, because the paper in particular, Darren Ford's paper, which is from 2007, which is the one that first worked out how to do these coefficients, was before the somewhat more modern understanding of what to do with the delta functions. But I think it is equivalent to, ultimately it's equivalent to what he did. So we now have a 3 torus that encircles the triple cut solutions. So basically the way we would proceed in a derivation is you'd write down a general parameterization of the loop momentum in terms of, for example, spinorial quantities. And we would do the integral around the T3, that it's essentially imposing the triple cut. Of course, we have 4 components, so there's one remaining degree of freedom. Let's call it T, which is the notation that Darren used. Remember that there's a Jacobian, well, it's been erased now, but there's a Jacobian in general that arises, that's the derivative of the polynomial in the denominator. And in this case, the Jacobian has the form of some constant in the sense of it doesn't depend on the loop momentum, depends only on the external kinematics divided by T. And that allows us, instead of leaving T to be determined by its original contour, which is somewhere well, it's determined by the real contours of the original loop momenta. So it would have naively some contour if we were trying to do the integral, but we're not trying to do the integral. We're free again to replace that contour with a little circle about one of the two poles, which are at 0 and infinity. It turns out it's more convenient to think about the pole at infinity, at least to make a link with what Darren was doing, because if we have some numerator, so now in general, what's going to happen? We have a parameterization of L that depends on t. So when we plug that into the tree amplitudes, we're going to have each of these amplitudes is going to be a function of t. So this thing is now going to be a function of t. And it turns out that what we essentially need to do is a contour integral dt over t of this function of t. Now, this function of t still has boxes in it, but those boxes we know have solutions somewhere out in the complex plane. So a typical box is going to have two solutions. And there's some location somewhere out in the complex plane. And you can solve for them explicitly if you know the list of boxes. So what we want to do is actually just isolate, for example, the pole at infinity. And that's easier to do because, in fact, the form here will typically have a t for power counting. The thing that we're looking for is ultimately a constant term as t goes to infinity. So as t goes to infinity, these boxes will go away because they're scaling like 1 over t. And the residue that's left at infinity is going to give us the coefficient of the triangle. Of course, in general, again, the loop momentum can go either as t or as 1 over t. So the triangle, in general, if you ignore the contributions of the boxes, has terms that go anywhere from t to the minus 3 to t cubed. And the thing that we're interested in pulling out is the t to the 0 contribution. So the way you can do that is to define an operation which Darren called inf, which says take the polynomial terms as t goes to infinity. And then at the end of the day, what you're going to want to take is the t to the 0 term, which is the residue of the pole at infinity. So again, conceptually, it's the sources of the residues and the sources of the contours are a little bit different from the boxes, but the way things work out is the same. We replace some of the contours to get a triple cut. It turns out that that offers us the possibility of changing another contour to fully localize the integral. And as a contour integral, we could simply choose, for example, to do it around t equals infinity. Now, let me just say a couple more words about what happens in the numerical approach. So in the numerical approach, again, you could imagine just doing this contour integral, let's say, around 0 numerically. That's not numerically stable because you don't know really. I mean, you could compute and you could make the contour small enough, but in general, there may be oscillations that are due to the presence of these other poles, and it's harder to get them under control. So in a numerical approach, it's actually useful to combine this, if you like, this contour-based approach with a subtraction that's one of the ingredients in the OPP approach that Pier Paolo has been talking about. So the kind of thing you would do is you would take this product and you would subtract the boxes, which you already know because you've computed them before. This object is now going to have only a finite Laurent expansion, as you, let's say, around any fixed circle, and you can take one conveniently at t equals 1, for example. And so this thing you can actually apply. You can do the contour integral by doing a discrete Fourier sum, basically. And that's the way things are done in Black Hat. I realize that may sound a little bit sketchy to many people here, but I hope it at least gives you a flavor of how things work for other integrals.